Hi everyone, please let me know if you can hear me. Can you quickly confirm if my voice is audible, if I'm audible or not? Okay, so I think I'm audible, right? Now let's get started. Today we are going to study or we are going to just solve a few of the practice questions from GATE PYQ, and most of the questions we are going to solve are from Deadlock and file system, right? So those who are watching first time, let me quickly introduce myself. So I'm Sachin. I'm co-founder and instructor at GoClasses. I finished my master's from Indian Institute of Science, and after that I worked at Amazon as an applied scientist. I have got GATE L All India rank 33 in computer science. Right? So as I say, today we are going to discuss deadlock and file system. So when I'm saying discuss, so basically mostly we are going to solve just the previous year questions from these two topics, and I will also tell you some good insights of these two topics. Okay, so I can say this session is going to be insight plus PYQs. So I will tell you what is the file system, and I will tell you that there is some algorithm called Banker's algorithm in Deadlock. So I will tell you that what does this Banker algorithm actually do, and what do we mean by the shape sequence. Okay, so let's get started. Okay. Now, okay, I think there was one question that we wanted to solve yesterday. That question is from GATE 2020. So let's solve this question, and then we will probably move to our today's topic, which is deadlock, right? So let me first solve this question. What they are saying is that consider a paging system that uses a one level page table. So they are saying the page table is only one level, which means this is the flat level page table. So they are talking about the flat page table. Residing in the main memory and a TLV for address translation. So they are using the TLV. Okay, they are using the paging. They are using the TLV. So they are what they are using. Let me just write it: flat page table, and then they are using TLV. So each man memory, obviously man memory will be there. Each man memory access and these things are given. And then each page transfer or disk access is also given. Assume that TLV hit ratio is given and the page fault rate is also given. Now they are saying a dirty page has to be written back in the disk before required the page is read from the disk. So basically, what does this mean? If the page is dirty, has to be written back to a disk before the required page is read from the disk. So if in your main memory, if you have a page and that's not the page that you're looking for, I mean you go to the main memory and then you find that okay, that's not the page that you're looking for, and if that page is dirty, then you have to write it back. Okay, so you will go to the main memory, and if there is a page fault, which means that this page is not the required page that you are looking for, then in that case you will first check whether this page is dirty or not. If that page is dirty, you will write it back. If that page is not dirty, then that's not a problem, right? So that's what they are saying. Now they are asking about the effective memory access time. So they have given the couple of parameters. Okay, so let me write those parameters. They have given these couple of parameters, and then they are asking about the effective memory access time. That's what they are doing, right? So they are asking about the effective memory access time. Now let's just quickly calculate it. Please let me know if everything is good, right? Okay, now let's just calculate it. So first thing is what we are going to do as a first thing. So we are just going to see the TLV, right? So we will go to the TLV, which means, so this effective memory access time will, I will be just writing in two summations. Some time that that is taken if the TLV hit is there, plus time that is taken if the TLV miss is there, right? So what is the hit ratio, TLV hit ratio? I think 0.95. So I will say that time like this TLV hit time will be 0.95 into some time, right? So here I will be writing 0.95 into some time. So let me just do it, 0.95 into some time. Similarly here I will be writing 0.05 into some time. This is the time if TLV hit is there. This is the time if TLV miss is there. Okay, let's just do this. Now like let me write the time when TLB hit is there. If TLB hit is there, you are anyway going to the TLB. So 20 nanoseconds you are anyway going to take. Plus, what else you will do? Once the TLB hit is there, you will go to the cache, right? Okay, cache is not there currently. Let's not worry about it. So once the TLB hit is there, what you will do? You will directly go to the, since you have the physical address, you will directly go to the main memory, isn't it? Now, in the main memory, obviously, I mean, see, from here you will be getting the physical address and then you will go to the main memory. Now, in case of TLB hit, I'm assuming that there is no page fault, which means that you do not need to worry about the page fault. So, there will be a TLB hit. This is the time to TLB hit. Now, you will go to the main memory and main memory access time is 100 milliseconds, 100 nanosecond, right? So, this is TLB time. This is TLB access time. This is main memory time. So you get the physical address and then you go to the main memory, and like since it was a TLB hit, you will definitely find that page in the main memory. That's the first case. That's a very, very easy case, right? Now let's go to a different case where you have the TLB miss. So it is TLB hit time, TLB hit rate, or TLB hit probability, whatever you want to say. And this is TLB miss rate, right? TLB miss rate. Now let's calculate this time. If the TLB miss is there, so how much time you have anyway taken? Since you have went to TLB, you have anyway taken 29 seconds, right? Plus some more time. Now you will say that okay, since it was a TLB miss, where you will go? You need to find the physical address, right? You will go to the main memory to find the physical address, isn't it? Now, since in the question it is not given at all that the page tables are always in the main memory. So in case of page table also, there could be a, so see, I hope you are getting the flow, right? So this is the TLB miss, and in case of TLB miss, what I will do, I will first go to the TLB, hit or miss, right? I will be asking whether it is a hit, or I will be asking it is a miss. Now, if it is a hit, right? If it is a hit, then I will say that okay, since it is a hit, then in this case, I will directly go to the main memory and I'm done, right? That's all. Because I'm assuming that there is no page fault. In case of it, I get the physical address. Okay, I have the physical address and I have the physical address. So I will go to the main memory and I'm done. In case of miss, what I will do? I will go to the page table, right? That page table is in the main memory, right? Page table, I will go to the page table in main memory because I want the physical address, isn't it? Now there could be again two cases that page table in the main memory could be present or could not be present, which means maybe you can have the page fault. So this miss is called page fault, right? So let me write it. So maybe you can have a page fault. For page table itself, you can have a page fault, or maybe you cannot have a page fault. Let me know if that diagram is fine till this point, right? Now, see, in case of TLB miss, you have anyway spent 20 nanoseconds. Now, there could be a like you can say there could be a page fault, or there could not be a page fault, right? Now, tell me how much time you are going to take if there is no page fault. So, if there is no page fault, what you are going to do? So, it means if there is no page fault, and what is the chance of no page fault? So, here I will be writing. So, here you just have two possibilities. Either there will be a page fault or there will be no page fault, right? So, maybe I can just write it in this way. I hope till now this is fine, right? Now, 20 nanoseconds you have already taken just for the TLB miss. Okay. Now, let me write in this in two way. Let me write in this way. So, plus this will be, this is basically, let me write in the bracket. Okay. So, you are going to take this much time plus you are going to take some time if there is a page fault or there is no page fault. So, let me write what is the page fault rate. So, 0.01. So, no page fault means 0.90. So, this is no page fault, and then I will be writing some time plus there is a page fault, then I will be writing some time. Let me know if that diagram or that equation is clear. If there is a no page fault, okay, it's a good case, no page fault. Let me first write the good case. If there is a page fault, then I will be writing here. Is this fine to everyone? TLB hit is no page fault. Yes, that is true. I mean, as I said, it is a debatable, and in GATE they have taken that TLB hit is no page fault because the reason is clear. Why that is no page fault? Because in case of TLB hit, it assumed that the page is already there. Because if page is not there, if I have replaced that page with something else, then in that case I must have updated the TLB, right? Okay. So anyway, let me just continue with this explanation. Now, if there is a TLB miss, then there will be a case that you will go to the page table. Now again, there will be a page fault for the page table itself. Okay, I'm not even talking about the data. For the page table itself, let me just talk about it. And then if there is no page fault, which means that it is now I'm here. It means I found my page table, right? Found the page table. So if you found the page table, then you will go to the main memory and you will say, okay, you will go to the main memory. You found the page table. You found, this is equivalent of saying you found the physical address, right? So anyway, like either there is a page fault or there is no page fault. I think you are anyway going to the main memory, right? So you are anyway going to the TLB and you are anyway going to the main memory. So you can write this main memory time is 100. Okay, this 100 you can write at the both places. Why I'm doing so? Because this 100, if you, or I can just separate it out. Maybe if you want, I can write this 100 here, because just to find this page table, you are anyway going to spend 100. Maybe there is a page fault, may not be there is a page fault, right? So 100 will be on the both the places. Okay, so I hope you understood this. Now if there is no page fault, then you got your physical address, you will go to the main memory, right? Okay, so you will go to the main memory and then you will find your page. So basically this 100 plus 100. So this 100, the first 100 is for your page table, and the next 100 is for your actual data, right? So till now we just got the page table. It is main memory. So this is for the page table basically, and this is for the data, right? Okay, let me know if that is clear. Okay, let's just read this question. Okay, sorry. They are saying that page table is residing in the memory. Okay, that's where I got just tricked. So yeah, so there will not be a page fault actually for the because for the page table, because page table is residing in the main memory. So there will no page fault at this moment. Okay, I'm sorry about it, because in the question it is given that that page table is in the main memory. So from here you get your physical address, and now you go to the main memory, right? Now you go to the main memory and then you go to the main memory again. Then you ask whether there is a page fault or there is no page fault. So there is no page fault or there is a page fault. Okay, so let me just a second. So let me just quickly tell you that we have been doing. If there is a TLB hit, then life is very simple. TLB plus main memory. That's the only time I'm going to take TLB plus main memory. If there is a TLB miss, I will go to the page table, right? If there is a TLB miss, then anyway I have spent the time for the TLB, and then I will go to the page table in the main memory. So let me write plus 100 also, right? So plus 100. Why I'm writing plus 100? Can anyone tell me? So see, if there's a TLB miss, then in this path also you have went to TLB, you went to the page table also, you have went to the TLB. Okay, this is in case of TLB miss, this is the TLB, and then for the page table in the main memory, and that's always there. That's what they are saying. That page table is always in the main memory, right? They're saying that, like, I mean, you cannot have a page fault. That's what they are, that is given to us. Okay. So Ratul, can you send that question to me on the Telegram? I will check the context. Okay. Okay. So let me know if that is clear to everyone, that in this path also you will be going to the TLB and then you will be going to the page table. So till now, I hope that everything is fine. Now you will go to the main memory again, right? So maybe I can write in this way, maybe plus 100 also I can write. Okay. So maybe because see, you are going to the TLB, you are going to the main memory, and then you are again going to the main memory. Then it depends on then, like, I mean, since this is common, so you can write it there, or maybe if you want you can write it in the both the places, which means in case of page fault also you have just went to the main memory, because that's how you got that there is a page fault. And in case of no page fault also or page fault also, you will go to the main memory. See what is happening. You get the physical address. Till this point you just get the physical address, and then you go to the main memory with then, I mean, there will be a page fault or there will be no page fault, then you are anyway going to the main memory, right? You one time you will definitely go to the main memory. So if you want, I can write the 100 here. Okay, I mean, you can write the 100 inside also, you can write the 100 here also, anywhere is fine. So what do you suggest me? Should I be writing inside or outside? Maybe. So both are fine, which means you can write the inside 100, because you are anyway going to, or maybe let me just do one thing. Let me write inside for now. Okay. Is there any particular suggestion that you have? Okay. So let me just copy it. Okay. Maybe I can write it outside, because that equation will be little shorter, right? So plus 100. Why? To go to the main memory, and then I will be saying that, okay, either there will be a page fault. If there is a page fault, then there is no page fault, then what I'm going to do? If there is a page fault, then what I'm going to do, right? So that's what we are calculating. Now tell me, if there is no page fault, which means you are currently here. You went to you have the physical address. You went to the main memory. If there is no page fault, then what you will do? I think you are done, right? So you are done. So what I should be writing here? 0.90 into what? So if there is no page fault, it means you are done. I mean, you do not need to do anything. So should I be writing here something, or I should leave it as it is? So you can write 0. I mean, you do not need to do anything, right? So if there is no page fault, you don't need to do anything. It is just 0. Now, if there is a page fault, then what you need to do? Can you tell me? If there is a page fault, then it is given in the question that if there is a page fault, then in this case you have to, with some chances, with the dirty pages with 20%. Okay, yeah, 20% chances are there. If there is a page fault, then 20% chances are there. You have to write the dirty page, which means if there is a page fault, then you will say that if that page that you want to that is there instead of your page, is this page dirty, right? Dirty page or not? If yes, if no, if yes. Okay, if there is no dirty page, it means the page is clean. What you will do? You will bring some page from the disk to the main memory. Okay, so now here you will say if the page is dirty or not, right? So you will say, if let's suppose the page is not dirty with this much hit rate, okay, page is not dirty, then what you will do? And if page is dirty, then what you will do, right? That's what we need to check. Okay, this is very big question, but anyway, let me write page is dirty. Okay, I hope it is visible to everyone, right? Now let's just check that what's going to happen if page is dirty or page is not dirty. So if page is not dirty, then what you will do? Can you tell me? If this is not a dirty page, which means you will go to the secondary memory. You will go to the secondary memory. So anyway, in both the cases, you go to the secondary memory, but that is fine. You go to secondary memory, secondary storage. Bring that page in the main memory, and that's what it is given to us. That the transfer from one page from the hard disk to the main memory, it is going to take 5000 nanosecond, right? And then once you get it, once you bring this page, what you need to do? You will say that, okay, finally you found your page, and then you will just return from there, right? So which means if page is not dirty, then can anyone tell me what is the time that I am going to write it here? If page is not dirty. So I will be writing 5000, right? Why? Because this is the time that I'm going to take just to transfer the page, 5000. And once I transfer, go to hard disk, transfer the page and done. Transfer, and then I will say done. If the page is dirty, then what I will do? I will write that page. So there will be, here you have just one IO operation. Okay, that is called write operation. Okay, one IO operation. Which is a write operation, right? If page is dirty. So if page is not dirty, then yeah, so you are going to write, sorry, read. This is called read operation. If secondary memory to the main memory, this is called read operation, because you are reading the page, right? Read operation. But if page is dirty, then you have to write that page, write dirty page plus read required page. There are two operations you need to do: write dirty page plus read required page. So it means that you are going to take 5000 plus 5000 here. 5000 plus 5000, right? Okay, I'm not sure if that is very much clear. So that's why what we will do, we will just just resolve this question one more time. Okay, let me do it quickly this time. See, we want to calculate the effective memory access time, right? Cool. So let me write it here: effective memory access time. Now what we will do, we will first go to, just check here, we will first go to the TLB. Either, I mean, I mean, you are going to the TLB, so you can anyway write this 20, and then you will say that, okay, plus, then there will be a TLB hit or there will be a TLB miss, right? Now again, yeah, that is fine that you are also going to the main memory, but if you want, you can take the common things, common things at first, which means what is common? Maybe in all the paths, either you go to the TLB hit or TLB miss, the main memory is common, and then, okay, in case of miss, there are two main memories and one hard disk, that is common, right? Okay. Anyway, let me just go in this flow. So you are going to have a TLB miss or TLB hit. So let me just write TLB hit, and this is TLB miss, right? So you are going to take 0.9, 0.95 and 0.05. This is the hit and miss time. Now, if this is TLB hit, how much you are going to take? You will just go to the main memory, which means 100 more, plus into 100. If this is TLB miss, then how much you are going to take? If this is TLB miss, you will go to the main memory for the page table. So that you will always find, right? So that will be just 100 for the page table. And then you will again go to the main memory, right? I mean, now again you are asking a question whether it is a it will be a page fault or no page fault. So anyway, you will again go to the main memory, and then now the question will become, it is a page fault or not, right? So now you will be basically dividing your path, right? So here you will be having 2 times. So maybe what I can do, I can write this whatever you have here with the page fault, okay? I can write it here. So let me write this page fault or no page fault. Page fault deal time I'm writing. So it will be, if there is a page fault, if there is no page fault, let me write it first, 0.90. So if there is no page fault, then anyway you are going to access this main memory, right? So we have write the main memory for page table. Okay, we have write this main memory we have already written. So let's not write it. So okay, if there is no page fault, then I don't think we are going to do anything. If there is a page fault, right? If there is a page fault, then what we are going to do? We are going to check if the page is dirty or not. The page is dirty with 20% chances, okay, and 80% chances the page is not dirty, then you will just spend 5,000. Plus page is dirty with 20% chances, then you will be spending 5,000 plus 5,000. Right? So once this flow is clear to everyone, right? Once this flow is clear, then you can easily write the equation in any way, right? I mean, you can write in this way. Maybe in the earlier case, I have taken this 100 outside, and in this case, 100 and 100 I have taken two times, but you can write it outside also, right? Once this flow is clear, then you can write the equation in any way. Okay. So I hope that is fine, and let's just check their answer. So I think like in whatever way they have written, it must be the same. The final answer should be the same. Okay, so you can just calculate it. But this flow should be clear. Now, if the flow is clear, then you will be understanding that how to write the equation. Right? That's very easy. Either TLB hit. In case of TLB hit, you are going to take this much time. In case of TLB miss, you will definitely take this much time. And okay, till this much time you are definitely going to take. And if this is page fault, then okay, nothing else. If there is no page fault, then you can write it. So can you do one thing? Can you write the shortest equation that is possible? Okay, with this, let me just go here. With this diagram and with this diagram and the given information that is here, can you write the shortest equation? Let me quickly write it. Okay. So in case of TLB hit, see, you are anyway going to take, okay, let me just write these things. You are anyway going to take this 20 for the TLB. And I think for the main memory, you are going to take this 100, right? In both the cases. I mean, either it is for page table or what. So anyway, you are going to take, this is for both the cases. So I think now, like till this part it is done. Now if it is miss, then there is something extra, right? So now if it is miss, which means the miss TLB miss rate is 0.05. Now there is something extra. If this is miss, then the something extra begins from here, right? So anyway, you are going to have the main memory, which is 100 plus, okay, if there is no page fault, you are not going to do anything, plus if there is a page fault, so the page fault rate is 0.01, 0.1, 0.10. If there is a page fault, right? If this is with page fault, then if it is a dirty page, okay, then if it is a dirty page or not, I mean, one hard drive you are anyway going to take, which is 5,000, right? 5,000. And yeah, I think that is done. If that is not dirty page, if this is a dirty page with 0.20, and then you are again going to take the extra 5,000, right? Right. So I think this could be the shortest possible possible equation. right? Yes. So maybe you can try writing this equation directly, okay? Or maybe like first thing is that you should be making the flow correctly, and then once the flow is clear, then you can just write the equation in any way. Okay. Now let's move to other topic of today. I mean, the today's topic itself is deadlock and file system. So let's just see the deadlock in a very brief way that is required for the revision purpose. Okay. Now there will be some different type of question that that is asked in deadlock. One is that they will give you the resource allocation graph, and they will say that whether the system is in deadlock or not. That question has been asked in GATE 1994. So what you can do, I mean, definitely you can make some matrices like available, need, and these things, but maybe just by observation also you can do this question. How? You just check that P2 is asking for R2, and then one of this R3 is free. I mean, P2 already is R2, one of this R3 is free, right? So what you can do, you can give this to P2, and then you can say that, okay, all of this P2 is done. I mean, P2 is now, you can just remove the P2. Why I'm removing the P2? Because you can give this to P2, and then P2 will say that, okay, I'm done. Okay, let me just remove some of the processes. Maybe it will be, you will get it that whether the deadlock is there or not. So P2 is done, and now one of the resource of R2 is also free, right? Once the P2 is done, one of the resource of R2 will be also free. So you will say the first you can done P2, you can do P2, and then let's look at this P3. P3 is asking for two resources of R2, so currently I cannot give. P note is asking for one resource, okay, one resource of R3. I think I can give it, right? So I can give it to P note now. So P note will also be done. After this, P note you can do because it is just asking one resource. So P note is also done. Okay, sorry. Yeah, one resource of R3 and one resource of R2. I can fulfill both. So that's why P note is done. Right? Okay. So now you will say once the P note is done, let's just check if you can satisfy this P1 and P3. So P1 is saying I'm looking for one resource of R1, and that you can definitely satisfy. So that's why you will say P1 is done. And then once P1 is done, this resource will be free, and then you can also do the P3. Right? That is how you can easily execute it in this order. So that's why this is not in deadlock. So sorry, not in deadlock. Let me know if that is clear to everyone. Okay. Now let's just look at one algorithm which is called Banker's algorithm, and that is very popular algorithm in this deadlock. So here my idea is not to just calculate the Banker's algorithm. I mean, you must have already done this Banker's algorithm, but my idea in this particular session is to make you understand that what this is doing, especially that what is the safe sequence. Okay, you do not need to remember that this is a safe sequence. I mean, you should be feeling it, like what is the safe sequence. Let's just see that what is a safe sequence. So before that, let's just see what does this Banker algorithm do. So before granting the resources, check if the resources state, resulting state is the safe state or not, or the safe sequence is not. If that is a safe state, then there is no deadlock. I mean, you can definitely grant it. Otherwise, wait. So what does this mean of saying the wait? Can anyone tell me that what does it mean of saying wait? What will happen if you are going to wait? So if the Banker's algorithm is clear to you, then you should be able to answer this question. If the Banker's algorithm is in little bit of doubt to you, then you may not answer this question perfectly. So tell me, what does it mean to say that that we are going to wait? So let me just clarify this thing, and then you will get to understand that what is the safe sequence, what is this Banker's algorithm is doing. Okay, let's take very naive and very simple example. Suppose there are 12 tape drives that you have, and there are three processors P0, P1, and P2. Currently, they are using like P0 is using 5, 2, and 2, and they can ask in future they can ask for 5, 2, and 7. Right? So I mean, they could ask, this is the maximum. So I mean, the terminology here is that this, we call it, this is the maximum, right? Okay, so how much you have in your hand? So this is called basically available. This is the terminology that we use. Available means that this is the allocate. This is what we call allocated, right? And then we say that okay, this much allocated and 3 are remaining. They can ask in future 5, 2 and 7. This is the maximum thing that they can ask, right? Okay, I mean, yeah, this is the maximum they can ask, and there is something also called maximum need, and that like maximum need we are calculating by this. So we are saying the maximum need of this is 10. They are using currently 5, and in future they can ask 5. Now current state is safe because there is just a sequence. What I can do, I have 3 available. Even if this they ask, so this is the maximum they can ask, right? So this is basically, this is called need or maximum need, and this is like maximum they can ask in future. This is the maximum they can ask, maximum requirement you can say, right? So if they ask for 5, see currently I have 3 available. If P not asks for 5, I may not be able to give it. But if P1 asks for 2, I can give it, and then I will be having 5. Then I can give it to P naught, and I can give it to P2. Is this okay to everyone? Now we need to understand this bit more carefully, that what does this max mean, and what and how we are calculating what we are calculating. All of this we need to understand a bit more carefully. Okay, so let's just understand it a bit more carefully, that what we are doing in this case. See here, what we are saying, that maximum you can ask for, maximum they can ask for 5, 2 and 7. But is this the case that they will always ask for 5, 2 and 7? No, right? I mean, this is the maximum that they can ask, maybe at this point in time, right? At, let's suppose this is 10 a.m. currently. At this point in time, this is asking 2, this is asking 1, this is asking 0. Maybe this can happen. At 11 a.m., this can ask 3 more, this can ask 1 more, this can ask 5. At 12 p.m., they can ask 0, it can ask 0, it can ask 2 more, something like this. So what I'm saying is that, I mean, this is the maximum that they can ask. It doesn't mean that they will ask all of this at the same time, right? I mean, this, I'm just being very calculative, and in this case I'm saying that okay, even if they ask at the same time, at the 10 a.m. itself, okay, at the 10 a.m. itself, if they ask all of this, then also I'm ready. That's called the safe sequence. Safe sequence means that even if they ask for their maximum at the same time, then also there is a sequence which can satisfy all of the request. Is this clear to everyone? Okay, I mean, I will tell you in a bit more detail what does the safe sequence mean, but let me know if that is clear to everyone. That safe sequence here means that even if they ask the maximum at the same time, then also I can fulfill, right? Okay, now, but in reality, what may happen? This may ask 2, this may ask 1, this may ask 0. You have 3 available. Can you not satisfy it? Let's suppose they are not asking this at 10 a.m. itself. At 10 a.m. they are asking 210. Okay, can you not satisfy this 210 request at 10 a.m.? Which means, can you not satisfy this P naught first? Okay, see, the safe sequence is P1, P naught and P2. And what does the safe sequence mean? Safe sequence is P naught, P1 and P2. And what does the safe sequence mean? Even if they ask the maximum at the same time, then also I can satisfy all of the requests in this order. That's what it means, right? So even if they ask, that's the point here, even if they ask. For maximum at the same time, then also we can satisfy the request. This is called safe sequence order, right? I hope you understood this. Now let's just see that that what if instead of if P not ask for let's suppose 5, then sorry, this is P1 P not P1 P not and P2, P1 P not and P2. Okay, if P1 asks for let's suppose 2, then can I give? Yes, I can definitely give. And after it, okay, after P1, if P not asks, then I can give. If after that, if P2 asks, then I can give. But what if? Okay, this is the safe sequence that you have. What if? Okay, this is the safe sequence you have. What if P0 is asking maybe some resources, not maximum, need not to be maximum, but if let's suppose this is the safe sequence you have. Let's suppose if P0 is asking for one resource, can you satisfy? At this point in time, okay, P0 is asking for one. You have three available with you. P0 is asking for one. This is the maximum that it can ask. P0 is asking for one. Can you not satisfy? Maybe you can satisfy. I mean, it depends whether the resulting sequence will be the safe sequence or not. I'm not saying that you can always satisfy, but I'm also saying that it's not that you cannot satisfy, right? It depends whether the resulting state is the safe sequence or not. Okay. So what I'm saying here is that this is the safe sequence. It means that you can definitely, if P1 asks, okay, if P1 asks first, then P0 asks, then P2 asks, I'm very happy. Because even if P1 asks for the maximum I can satisfy, and then P0 asks for the maximum I can satisfy, then P2 asks for the maximum I can satisfy, right? So that's what we can do. But let's suppose if P0 asks, instead of P1, if P0 asks for some resources, P0 asks for some resource, then can I satisfy? The answer is it depends whether the resulting sequence is safe sequence or not. Which means, let's suppose if P0 is asking, let's suppose P0 is asking for 3 itself. Okay, it can ask 5 at max, but let's suppose it is just asking 3. Then can I give? May not be, right? If I just give 3, I will be having 0. Then in the future I will not be able to satisfy any of the request, because P0 is waiting, P1 is waiting, P0 is also P2 is also waiting. So if P0 is asking 3, may not be, right? But if P0 is asking, let's suppose 1, maybe the resulting state is safe after it, right? So it depends. I mean, see, the safe sequence doesn't mean that I will always satisfy in that order. It only means that this is the order that is possible even if they ask for the maximum. And okay, and if some other process, let's suppose P0 ask for some resources, okay, if P0 ask for some resources which is not in the safe order, I mean not in the order of the safe sequence, then can I satisfy? May or may not be. May not be. It depends. You can say it depends if resulting state is safe or not. Okay. If P2 asks, maybe I can give. It's not like I cannot give. Maybe I can give. So what do I mean by saying wait? Okay, here what do I mean by saying wait? If this is not safe, I mean if someone is asking if it is not a safe sequence, then what will I do? I will ask them to wait. Why I'm asking them to wait? Let's suppose the safe sequence order is P1, P0 and P2. P1, P0 and P2. Let's suppose this is the safe sequence. Now suppose P2 ask for some resources, okay? Some resources. And we are asking it to wait. Why? Because and let's suppose that after I mean, let me write it. We cannot give. We can't give because resulting state is unsafe. Right. Now my question is that, I mean, that is fine that we can't give because that is unsafe and all. Now my question is that why we are asking for P2 to wait? Okay, why we are not killing P2 or something? Why we are asking for P2 to wait? P2 is asking some resources. I cannot give them resources, and I'm saying, can you wait? My question is that why we are asking it to wait? If I cannot give, maybe I will say that okay, let me just maybe hold this P2 or something. Then let me just restart the P2. Okay, why we are asking it to wait? What will happen after some time? Wait means that wait for 5 minutes, wait for 10 minutes, wait for 1 hour, something like that, right? So what will happen after 1 hour? Okay, why we are asking, or maybe let me write it in that way. What will happen after some time? Why we are asking it to wait? Can anyone answer this question? See, the interesting part here is that that we are asking it to wait because we are 100% sure that there is a safe sequence, right? We know a safe sequence exists, which means we will say that, okay, if you are asking me some resources, can you please wait? Let me just finish the P1 first. Let just P1 ask for something, and then once P1 finish, then I might give you. I mean, maybe let me ask. Let me just wait for the P1. Once P1 finish, then let me just wait for the P0, and then once both of this finish, then I am 100% sure that I have the available resources to give you, right? So basically this is the safe sequence, which means that P2, all of the sudden P2 is asking, then I may or may not give. If I'm giving, that means it is a safe sequence, a resultant state is the safe state. If I'm not giving, it means that I'm asking them to wait. I'm asking P2 to wait because I'm waiting for P1 to finish, I'm waiting for P0 to finish. Once they are finished, because once they are finished, then I am 100% sure that since this is a safe sequence, then I must satisfy the P2 request, right? Okay. So I hope that is fine with you, right? Now, uh, now let's just do one thing. So I hope you understood this. Now let's just continue this in this particular example. So we have just checked the given state is a safe state, right? Now suppose P2 asks, see, what was that state? That state is P1, P0 and P2, right? This is the state. Now what they are saying, suppose this is the state. Now what they are saying is that now suppose P2 requests one drive, right? I mean available is 3 with you. You have the 3 available, right? And if it is asking for one drive, then P2, then would the resulting state be safe? So basically, in other words, let me just ask this question: if P2 requests one drive, then can we give one drive? Then can we give one drive to P2? This is my question. Are you getting what I'm asking? See, there is a safe state, which means if P1 asks, then P0 asks, then P2 asks, I'm very happy. But suppose P2 is asking all of the sudden, instead of P1, P0, P2 is asking all of the sudden, that is just for the one drive, right? Then can we give one drive to P2? It depends whether the resulting state is safe or not. So let me just check, right? Assigning one resource to P2. If I assign one resource to P2, then this 2 will become the currently allocated to this 2 will become 3, and the available will become 2, right? Available will be just 2. Now just check if this is a safe state or not. Okay, I don't think it is a safe state because this 2 I can satisfy this P1, and then there will be just 4, and then I will not be able to satisfy any of this, right? So the resulting state is unsafe, right? So that is why I will not assign, right? It depends. If I can assign or not. It depends the resulting state is safe or not, right? I hope that's fine with all of you. Okay. Now, so I hope you understood that what does the safe sequence mean. Now, can you just solve this question? What they're saying that let P1, P2 to Pn be the only safe sequence, okay, safe state or the safe sequence of the system, then which of the following is or are always true? That is a MSQ question. This question is Go Classes test series question. I have put this question just to make you understand that what does the safe sequence mean. So generally we put the question only when we think that there is some concept behind this question, right? So suppose this is the only safe sequence that is there. Then they are saying if P2 is the first process to request for some resources, then P2 always have to wait. Is this true or false? Let's suppose all of the sudden P2 is asking. See, P1, P2 and Pn, this is the only safe state. But let's suppose all of the sudden if P2 is asking, then can I give something to P2? Unsafe state means that if I give, then I may go to the deadlock or may not go to deadlock. Unsafe means that it is a risky. Okay, unsafe doesn't mean that it is always a deadlock. Right? Unsafe means it's a risky. Tell me if this A is true or false. If P2 is the first process to request, then it always have to wait. No, right? I mean, maybe it depends. If I can give that to P2, give some resources to P2 or not, it depends if the resulting state is safe or not after giving it, right? So that's why this is a false. Yes, Akash. That is a false statement, right? So that is a false statement. Why? Because it depends whether after giving some resources to P2, whether the resulting state is safe or not. That is why it is false. Let's go to this. P1's request will always be satisfied without even checking if the resulting state after processing P1's request is in the safe state or not. So they are saying that that if P1 is asking for something, then I can always give that to P1. Then I can always give that to P1. Tell me if this is true or false. See, P1 is in the safe sequence. So if P1 is asking something, then why not, right? I can always give that to P1. Even if P1 asks for the maximum, then also I can give. Okay, even if P1 asks for the maximum, then also I can give. That's the beauty about the safe sequence. So that is why it is true. That is why this particular option is true, because even if the P1 asks for the maximum, then also I can give. What about C? Processes request will always be satisfied in the same order as the safe sequence, and we cannot satisfy any out of order process request. Is this true or false? Okay, let me know. Yuvraj, Akash, Devaranjan. So I think this is false, right? I mean, we can satisfy out of order request. It depends whether the resulting state is safe or not, right? These things we can never satisfy any request coming from Pn without satisfying request from P1. We can never satisfy. They are saying we can never satisfy. So that's also false, right? It depends whether the resulting state is safe or not. So that's why it is also false. Okay. So I hope now you understood that what do we mean to say the safe sequence, right? So that's what we mean to say the safe sequence. Is this clear to everyone? See, this is very important to understand that what we are doing, right? Instead of just memorizing something, we should be knowing that what is the safe sequence and all. It doesn't take much time just to understand the things. Okay. So actually in Deadlock, to be honest, there is nothing more. I mean, we can solve one question if you want, but there is nothing more. We like the way we have solved this question, and in the same way we can solve the question which is having the multiple resources. So let's just quickly solve this question, and then we will go to the file system, right? So what they're saying that allocation. Okay, it has already been allocated. This is the maximum that they can ask, and this is the available with you. So every process ABC, every resource ABC has some available with us, right? Now, is this a safe or not? So I think this is safe because we can satisfy P1, because P1 will be asking, see, this is 322, right? So P1 will be asking the maximum it can ask 322, and we already have 332. So I think we can satisfy P1. And then once we satisfy this P1, then this allocated 200 will be added, right? Because that is done. Then 532 I will be having, and then I can satisfy P3. P3 is asking 222, so I can satisfy this. So that's why it is a safe sequence, right? Now, if P1 asks again, okay, this is a safe sequence. Now tell me, in this safe sequence, if P1 asks something, do I even have to check that whether the resulting state is safe state or not, or I can always give? I can always give, right? Because even if P1 asks for maximum, then also I can give, right? Now suppose that P1 requests for something. See, P1 can request maximum this, right? But suppose that it is not requesting for the maximum, it is requesting for something lesser. Then also it is fine. I mean, then also it is fine. Even if it requests for the maximum, then also I can satisfy. So I do not need to worry about the P1, right? I do not need to worry about checking the P1. Now, suppose in this state, P4 requests something which is 330. If P4 is out of the order, then I have to check, right? Then I have to check. Okay. Is this clear to everyone that what we are doing? right? If P4 is out of the order, then I have to check. If P1 is asking something, then I do not have to check. So anyway, we can solve any of this question using the banker's algorithm. And now I hope you understood that what does this safe sequence mean. So I just designed this question in such a way that if someone has truly understood the safe sequence, then only you can answer this question. Otherwise, you will not be able to answer this question. You will find this question in one of the mock. Okay? In one of the mock, you will finding. I'm sorry if I revealed this question, but I had to do it because I had to like solve this question in one of the video to make you understand more. Okay. Now let's just start file system. And please let me know if there is any doubt till now. Okay. So in the file system, we are going to study a few file system implementation techniques, right? And we are going to see some of the questions based on the file system implementation technique. So please let me know quickly, should we do it now or should we do it tomorrow? Anything is fine. I think we can do it now only, right? Okay, let's just see. So what is a file? File is some data. I mean, it is just everything in the computer is just zeros and ones, right? So data in some format. And some format means it could be a PDF file, okay, could be .pdf, could be .jpg or something like that, right? So what is a file system? It provides a way to store the file, right? It provides a way to name the file. It provides a way to store or metadata of the file and so on. So basically, see here, there will be a disk. On this disk, we are going to store a file. Now, there are two things in the file management. Okay, in the file management, there are two things. One is that hardware part. One is operating system part. Okay, which means hardware part means how disk is organized, how sectors are organized, everything, how disk, sectors, these things are organized, right? If you have studied our like go classes, I think in the dbms itself, Deepak has discussed it, and I'm 100% sure that you must have got the feeling of the disk and sectors in that lecture, right? Deepak has actually shown every variation and why. Like he has actually taken the counter examples that if we store the file in that way, then what is the benefit, what is the disadvantage? If we store the file in some other way, then what is the advantage, disadvantage? He has talked about seek time, rotation time, everything in very very detailed and illustrative manner, right? So I'm sure about it. Okay, and about this OS part, we are going to study today, right? This is the topic of discussion today. So what do I mean by the OS part? So there's a hardware on which we are going to store this file. This software part that tell that how to store the file. OS part means it will say that, okay, how to yeah, basically, like, file system implementation is just telling you that how to store the file, in the sense that whether the file you are going to store in a contiguous way, different linked list way or something, right? So how to store file. So here you will study about the hardware part, that is generally in computer organization, or we have taken this in dbms, because in dbms also, like, it can be taught. So in one of the lecture in dbms, Deepak has taken it in very good way, and then like in this os we are just going to see how to store the file. So when I say store the file, there are few difficulties that we have, or few challenges, right? So few challenges, or maybe let me just write the objectives with us. What are the objectives that you have if you are going to store the file in the disk, right? So what we are going to do, we are going to store a file in disk. Then what do you think, what are the objectives we can have? I think first objective, whatever way you can store, right? First objective should be your retrieval should be fast. Your retrieval I don't know if the spelling is correct, but anyway, retrieval should be fast. What do I mean by that? Maybe I mean, if you are storing some file, then where is that file? You should be calculating it quickly. It should not take too much of time to just go here and there, and you are just checking, okay, where I put this file. It is just like you are going to store something in a room, right? This is a room that you have, and here there are many almiras, and then in one of the almirah you are going to write something, right? You are going to put something. Let's suppose you have one box, you are going to put that box in the one of the almirah. Then it should not be the case if I'm asking for this box number, let's suppose 3. You should not be searching everywhere here and there, and then you are going to say, okay, I just forgot that where is this 3, let me just search in the entire room. It should not be the case, right? I mean, you should be efficient. You should be immediately telling me that, okay, where is the 3, right? So maybe it is just one of the objective. I'm not sure that we can fulfill that objective or not. But yes, this should be one of the objective. Is this fine to everyone? That this is just one of the objective that we can have. What is this next objective that you can have? Any other objective that you can, that is coming to your mind? So it is very analogous to saying that there is a one room in that very small sachets or small almiras are there, and you are going to just put a box there, right? The box is just file, and your room is your disk, and these are just sectors. I mean, small things are called sectors. Then what is the next objective that you can have? Maybe your file or your boxes should not garbled up, which means you should not put one box on another. I just want to want to put one box in just one of the almirah. So maybe you can say that you should not overwrite the files, right? If I'm writing some file at some location, I cannot write two files on the same location, obviously, right? So my files should not be garbled up, right? Or my data should be safe at least, right? My data should be saved. So your data should be safe, right? Something like that. So there could be, yeah, there could be many other objectives that you can think of. Definitely you can think of, but yeah, this is just to give you a feeling that what we are going to do. So now my objective is that what we are going to see, we are just going to see few ways. Okay, I will just tell you some ways, some methods to store file on disk. Now there will be many methods. Okay, I mean, there are popularly three methods. Method 1, let's suppose, let me just write them in this way. Method 2, method 3. Okay, so we are just going to see few methods, and then what we will do, then we will talk about the modern operating systems, right? Then we will check modern operating systems like Windows, Mac OS, Linux, like that, right? So we will talk about the modern operating systems and how they are storing the files, right? These operating system, if I'm storing something, then which kind of method they are using. So what I will do, I will just tell you some generic methods, and once these methods are completed, then I will tell you that, okay, this Windows is using, see, this Windows is using the method 1. I mean, this will be, since these are the very advanced technologies, they might be using some hybrid. So I will say that, okay, this Windows is using, maybe let me say that 80% of the method 1, 80% ideas are taken from the method 1. Let's suppose, okay, I mean, just giving you an example, 10% ideas are taken from the method 2, and then 10% ideas are taken from the method 3, something like that. I mean, what this is the plan of the lecture, that we are just going to see few methods, and then we will just compare these few methods with the modern operating system, that how these modern operating systems are getting actually implemented, okay, using these methods. So I will just say that, okay, see, this Windows is using some ideas from the method 1, some ideas from the method 2, some ideas from the method 3, right? So I hope that that objective is fine to everyone. Now let's just move to next slide. So okay, so what are the directory and all? I hope you know it. Directory and file are same thing in case of Linux. Okay, so I'm not going too much of this. Yeah. Actually, this is a revision session, so I'm just expecting that you know inode. Inode is something that stores the metadata. Okay, so there is something called inode which stores the metadata. Now, there are files and there are directories also. So, directory is also a file. It is just a special file that is having some special bit in the metadata to set 1, right? I mean, if I say the bit is 1, then it is directory. If I say the bit is 0, then it is file. Otherwise, all the properties it is having just as a file. So I hope you got the difference between file and directory. There is no difference. It is just one bit. Okay, one bit that is telling that it is byte. It is the file or it is a directory, right? And what do I mean by the metadata? Metadata means what is the name of the file, who has written this file, what is the location, what is the size of this file, can I edit this file, is this editable or not, what at what time I have created this file, and so on, right? This is called metadata. And how we are going to store this metadata, as I said, in the inode. So these are just common ideas. I mean, this file, directory, inode, these are the common ideas. We have not started our any of the method, right? So now, metadata you might have seen like this. I mean, this is a screenshot of Linux. Oh, sorry, of the Mac OS. So metadata means like what is the when it last time opened and like that, right? So there could be many details. So basically, file or a directory is just a inode. Inode means metadata. It has the metadata and the actual data, right? And the actual data. That is a file or directory. Now, what does the inode of the file contain? Inode of the file contain the metadata, right? A metadata. So metadata means what is the location and everything. And one of the field in the metadata, this is the inode which contain the metadata. One of the field will be a pointer to the actual data, right? This is the real data. So this is how the file inode will look like. This will contain the metadata, right? All the metadata. So this is all the metadata. I mean, this whole thing is called metadata. One of the field could be just pointed to actual data. And what does the data contain? Data just contain data, right? There is nothing here. So data just contain the actual data. I mean, this is the actual data. So this is data, right? Like, I mean, this just contain the file. Is this clear to everyone? That what is this inode and what it contains? Let me quickly know if that is clear. Okay. Now, Now let's just see that what does the inode of a directory contain. See, directory does not have its own data, but I mean, a directory just have different files. So inode must contain the metadata. Okay, location and everything is okay. But earlier I used to have the pointer to the actual data, right? Pointer to the actual data. This was the earlier picture. But do I have the actual data of the directory? Do directory contain the data? No, right? So basically, instead of the actual data, here I have, I mean, the actual data itself is called inode table. Okay. So here, what do I have? Here in this directory, let's suppose that I have few files. Let's suppose foo. Then I have few files. Let's suppose bar, and there are few files, right? And foo.c, bar.pdf, something like this. Then I will tell, okay, this is the file name, and this is the inode number of that file, right? Let's suppose this is 19, this is 31, something like this. So I will say that, okay, this is the inode number, this is inode number. So every inode has some number. Once I get the inode number, then that is very easy to calculate where is this inode is present. I mean, the physical address of the disk is very easy to calculate, because generally in the disk, all the inodes are one by one. So let's suppose the inode is starting from 1, then this is the first inode, this is the second inode, this is the 19th inode, this is the 31st inode, like that. So all the inodes are just one by one in the disk. Okay, I mean, that's how we generally organize the disk. So once I get the inode number, then it is very easy to get the disk address. Okay, anyway, I hope you understood this, right? So what does this data of the directory contain? Data of the directory contain the inode table. Is this clear to everyone? Okay, I hope that is fine, right? Now, this is how it looks like. The inode of the directory will look like this, and it contains the inode table. Once I get the inode table, I might be going to that particular inode of that file, and from that file I will be going to the data. Is this whole linking is clear to everyone? This is the inode of the directory which contains the inode table. I mean, one of the pointer may be to the inode table, and then from here I will be getting 18, right? Let's suppose I'm interested in this file. I will be getting 18. I will go to the inode 18, and from there I will go to the data of this food. This is the complete linking. Okay. Now, now I hope that is clear. Now it is not necessary that this kind of linking is there, which means what I may have, okay, instead of I mean, instead of this kind of thing, I mean, it is depending on the implementation. Tell me if I can have something like this. If that is let's suppose inode of the directory. Okay, in the inode of the directory itself, can I have something like this? There will be a metadata. Okay, some metadata is present here. And instead of a pointer to the inode table, can I just not store the inode table here itself? 218, something like this. I'm storing the inode table here itself. Can I do it? Yeah, it depends. It depends on the implementation. We can also store inode table. It is very important, and in fact in most of the questions it will be given that inode table is stored in the inode of the directory itself, or it is a pointing. I mean, if that is relevant to the question, they will give you, right? So we can also store inode table within inode of the directory. Okay, I hope that's fine. Now just our last point, okay, about it, which is that generally instead of calling it inode for a directory, we just call it directory. Okay, and for the files, yes, we call it inode, but for the directory, instead of calling it inode for a directory, we can also call it directory. Okay, so either you write inode for a directory or you write directory, both are same. I mean, generally people do not explicitly mention that this is inode for a directory. I mean, by default, like I'm saying the directory, it means the inode for the directory. Okay, because directly just have inode, it doesn't have any other data. So, and all of this, let's suppose I'm calling it directory and the inode table itself is in this, then they are not calling it inode, they are just calling it directory. Okay, because that's all for the directory. That's all the information that you have. So in the Galvin, if you go to the Galvin, they have followed exactly same notation, and instead of calling it inode for a directory, they are just calling it directory. Okay, and they are having the inode table inside it, right? So that's the notation that is followed in the Galvin. Anyway, I hope that is fine to everyone. So we are calling it directory, although it is inode, but for the directory we just call it directory, and in the directory itself we might have the inode table. Okay, cool. Now a short history of the directories. Maybe you can have a single level directory, you can have a two level, you can have a tree structure. So I'm not going to all of this. I mean, it's very easy. I will put it in the slide, you can just read out it. Okay, now let's go to the file implementation, which means how to allocate disk space to the file, which means how to store the file in the disk, right? That's what our agenda is. So here we will look at three methods, as I said: method 1, method 2, and method 3, right? Now let's just see this. How to allocate disk space to the file. There are few common allocation methods. See in the next slide. So this is the method 1, which is called contiguous way. The method 2 is called linked list way, or the method 3 is called indexed way. Okay. Method 1 is having one variation that is called extent based. Method 2 is also having some variation which is called fact table. Method 3 is also having some variation which is called multi-level indexion. Okay. So either you call 3 methods or you call 3 plus 3, which is 6 methods. Anyway, it doesn't matter. So we are going to study these 3 plus 3 or maybe just 3 methods, and once we study these 3 methods, then we are just going to correlate this with what? With the modern operating system. That's what our plan is, right? See, let me just recall you the plan. What we are going to do now, you have the basics of this directory inode and all. Now what we are going to do, we are just going to see these methods, and then once these methods are done, we are just going to relate these methods with the modern operating system. Then we will say that okay, some of the ideas are taken from method 1, some of the ideas are taken from method 2, like that, right? Cool. Okay, so now let's just look at the contiguous and its variation, linked list and its variation, index and its variation. Okay, So one of the method is contiguous, and let's just see what is this contiguous. It is saying that user specify the length and the file system allocates the space all at once. So all in the contiguous way. We are just going to allocate the space in the contiguous way. What does this inode contain? It has to contain the metadata. It will just contain the start location, starting location, and size of the file. By the start location and size of the file, you can actually calculate all the, from where the file begins, from where the file ends. So, one of the field in the inode will be like this, right? And obviously, it will be having a pointer to the first location. Where is this file stored? The disk number, block number. So basically, like let's suppose it is a block number 0, it is a block number 1, it is a block number 2. So it will say that okay, from the starting block is 2, start block is 2, start block is 2, and size of the file is, let's suppose, 10 blocks, right? So it will be containing these two information. Now, do you need to contain the address? Let's suppose it is having some address in the disk. Then actually you do not need to do it, because if you know the start block, if you know the block number to the address is very easy. How? You just multiply the size of the block, right? Whatever the size of the block, you just multiply to the block number. You will be getting the address of that, right? Size of the block. Okay. You can just multiply and you will be getting the address. Is this fine to everyone? Okay. So see here, it will be having base and this length is 3, right? Similarly this. And what is the disadvantage of this? Definitely the disadvantage is that it is leading to external fragmentation, right? So if some file C needs just 2 sectors or 3 sectors, I cannot allocate this C. So that's why it is called external fragmentation. Right? It is leading to external fragmentation. Let me know if that is fine to everyone. Now, let's just see a variation of it. See, there will be a variation of it that is called extent based, right? So, this is a variation of contiguous. Let's just see this extent based. So, multiple contiguous regions per file. So, what we are going to do in the extent based, we are going to say that in the contiguous we were very rigid, that it will start from here, it will end until this point. In the contiguous we were very rigid. In the extent based, what we will do, we will say that okay, if not exactly continuous, then maybe I will give some part here, okay, some part I will allocate here maybe, and maybe some part later, maybe some part here, which is called extents. Okay, these regions are called extents. These regions are called extents. So what I'm going to say, that if the continuous is not available with you, then you just put it some part here, some part there. Yeah, obviously, like it should not be too much of discrete, which means like you want your extent to be as large as possible. It should not be the case that extent size is just 1, right? Which means you are allocating here, you are allocating here, you are allocating here. Then it will not be contiguous. You want your extent size to be as good as possible, as large as possible, right? Theoretically, yes, this can also be extend, but you want your minimum extent size to be at least maintained something, right? Okay. I hope you understood this. So this is just like a contiguous, but some relaxation I am giving, that if exactly contiguous is not possible, then do it in two different contiguous regions, maybe 3 different contiguous regions, right? And the region is called extent. That's all. Now let's just look at one more method, which is called linked method, and then we will also look at one of this its variation, which is called fat method. Fat variation. So in the link method, what we are going to do, we are going to say that instead of allocating in the contiguous, let me just store in the linked list way, which means I will be storing some data here in this block. Block or sector both are the same thing, right? I will be storing some data here in this block or in this sector, some data here, some data here, some data here, and then I will be just linking them, which means the pointers I will be storing at the end of this block. I will be storing a pointer here, I will be storing a pointer here, I will be storing the pointer here, like that, right? So this is called linked allocation. So that's how we are going to store it, right? So in inode, I will be just having the pointer to the first block. This inode will be just having the pointer to the first block. Now, obviously, the disadvantage is that if you want to access this, then you have to do all of this the sequential access, right? So if you want to access some random random location, then it is not possible, right? Random access is slow. You don't know where is this sector. You have to go here, you have to find the next address, you have to find the next address, and then you will be getting this, right? So random access is slow here. Now I have one variation of it which is called fat variation, okay? And in like this is a short form of file allocation table. In short, it is called fat, but this is a short form of file allocation table. So what it does, okay, it is also used in MS-DOS, very early Windows operating system, and yeah, some of the maybe some of the ideas are taken in the latest operating Windows operating system also. Although the latest operating systems are using NTFS, new technology file system in the Windows, but yeah, some of the ideas are taken from the FAT also. Okay, so what is this FAT? It is just a variation of the linked list. So see, earlier I used to have this, right? Now also I will be having this actually. Okay, now also I will be having this, but there will be a small change. The change will be that I will be basically having one more table that is called a fat table. Okay, so earlier also this, now also this, but I have this extra now, which is called fat table. What does it contain? It says that okay, 6, this is the block number, sector number, 6 is linked to 4, which means some data I stored in 6 and then some in 4 and some in 3. Then 6, at the 6 I will be having 4, at the 4 I will be having 3, at the 3 it is the end of the file. So basically there is, I mean, this is just having the block numbers, right? This is just having the block number. Inside this I am just having the block number. So there is separate table that I am going to store in the disk that is actually having the pointers. Okay, that is actually having the pointers. You're getting my point? See, the way I'm storing is not getting changed. I'm just storing in the linked list way that I was storing earlier. It is just something extra I'm maintaining. And what extra I'm maintaining? Let's suppose I have 10,000 blocks total, 10,000 total blocks or sectors. Then I will be having 10,000 entries here. For each block I will be having one entry. And what it contains? It will be containing that it is linked to what next. 6 is linked to what next 4. 4 is linked to what next 3. 2 is linked to what next 1. 1 is linked to what next nothing. Like that. So for every block, what it is linked to. If it is not linked to anything, I will say okay, nothing. Right? So I will be maintaining a separate table. Now my question is that what is the benefit of this table? See, it's still doing a pointer chasing, right? It is still doing a pointer chasing. So what is the benefit of it? Can anyone tell me? See, I was storing as it is. I'm storing as it is as I used to store earlier. Now I just have an extra table. What is the benefit of this? I'm still chasing the pointers. But let's suppose I want to go to the third block, okay, or the second block of this file, or maybe the third block, or let's suppose there are different or there are more blocks. Let's suppose I want to go to this block, right? 1, 2, 3, 4, 5, 6. I want to go to the sixth block, right? Sixth. You getting my point? Let me know. So let's suppose I want to go to the sixth block of file. Then what I had to do earlier is that I have to go here, need to find second, need to find third, like that. Am I not doing the same thing here? I am doing, but not in the disk. I mean, what I will do, I will, since this is just a one table, I will bring this table in the main memory. Okay. In the main memory, I will be just bringing one table, just one table. And in the main memory, I can calculate that what is the location of the sixth block. I mean, what is this block number, right? I mean, I can do the pointer chasing. Like earlier, I was doing the pointer chasing, but that was in the hard disk. Now I can do the pointer chasing by bringing this table in the main memory just once. Okay, still pointer chasing, but now in main memory, right? If I want to go to the sixth block, I will just check, okay, where is the sixth? In just one read, I'm doing the same thing. Earlier, I had to read it. I have to bring it. See, bringing from something to main memory is called read. Okay, this is the hard disk. From here to the main memory, this is called read. I'm reading in the main memory. And if I have to write something, then it is called write. There has been gate PYQ. In fact, the latest gate PYQ is based on this concept only. This is called write. If I'm writing something, then it is called write. Do I have to write here anything? No, I'm just reading. I will just bring in the main memory. Do I have to store it back to the hard disk? No, I have not changed anything. So why to store it back to the hard disk, right? So that's why I will be not writing anything. Okay. So I hope that is clear to everyone. So I will bring all of this in the main memory, and that's why in just one read it is I'm doing the same thing. But earlier I have to bring this in the main memory, which means I have to read something from it. Then I will go, okay, I will get to know that, okay, this is the block number or this is the pointer for the next block. Then I will read it. Okay, I will bring that in the main memory, and that's all. That's all I will be keep on doing, right? So that's why it is too much of pointer chasing, but in the main memory. Okay, so I hope now you understood this, that what I'm talking about, right? So that's why we are using FAT, and FAT is very popular. There has been many gate PYQs that has been asking just using this FAT. Okay, it's still pointer chasing, but can bring the entire FAT in the main memory, so can be cheaper compared to the disk access. That's the point here. Now, okay. Now let's just do one thing. We are yet to solve 1-2 questions, and then we will be moving to our index allocation, right? So I will be just starting in the next video. Reason being is that, like, I don't want to make it too much stretch on one video. I just want to keep it little shorter. So since we are running out of the time, we will just start a few of the questions from the FAT, and then we will be just doing. We will just start in the index allocation, and then here also we had to do few of the questions. Then it will finish up your all of the gate PYQs. So we will be taking all of the gate PYQs. Don't worry. Okay, that has been asked in the file system. So all the PYQs that has been asked in the file system, I have in my slides. So I will just solving them. I will make you realize that this topic is very easy. Okay. So all the PYQs I have, that we will be taking it tomorrow. So thank you everyone. Take care. Bye bye. If you have understood everything, please just comment it out. If there is any doubt, just comment it out. If you have understood, then also please comment it out. Just keep on commenting so that we also get encouraged that, okay, we should be bringing more concept to the larger audience on the YouTube. Okay? So please keep on commenting.